Hey, welcome back to Calculus. In this short video, we're going to take a look at part of the material in section 10.3 on the polar coordinate system. In this first part, we'll just focus on the coordinate system and conversion between it and our rectangular coordinate system. In the next lecture, we'll think about functions in this new coordinate system. So you can see our goals there. We've got three of them. We want to introduce the polar coordinate system in the plane. I'm denoting the plane by this symbol R, R2, just denotes the plane where we draw our pictures. I want to be able to convert between these polar systems. Given a point in Cartesian coordinates, I'd like to say what it is in polar and vice versa. And then I want to be able to describe simple curves and regions in this new polar coordinate system, getting used to it. Real quick, I want to say something about mathematical dimension. What does dimension mean? Dimension in mathematics is the number, for us, a number of real numbers that it takes to locate a point in a space. So the reason that we call a line one-dimensional is because after you mark an origin, you mark a place where you measure from, then any point on a line is completely determined by a single measurement. It's by a single number, one dimension. All right, so look at the left-hand side of your screen here first. The plane is two-dimensional. The plane is two-dimensional because to determine the location of a point, well, we need two number lines. We usually call one of them the x-axis and one of them the y-axis. Where they cross is the origin. That's where we measure from. And you have to take two measurements, right? You have to measure how far along the x-axis you are, how far along the y-axis you are. So the plane is two-dimensional. It's why we put this 2 on the R. The R stands for the real numbers. The 2 means that we have two of them. And this coordinate system that we've been working in, the XY plane, people call that the rectangular, or sometimes it's called the Cartesian coordinate system after René Descartes, who supposedly formalized it. All right, so here's the launching point of the lecture. Planes are two-dimensional. To describe places in them, you need two numbers. Those two numbers don't have to be the rectangular numbers x and y that we're used to. Here's another way. So I need to tell you, where do we measure from? Okay, well, I'm going to pick a point in the plane and call it the pole. And then I choose just one kind of, not even a number line, but a ray. I'll just draw a line in one direction from the pole. It's called the polar axis. And then given a point in the plane, here are the two measurements that we're going to make. One of them, r, the number that we'll write first in our coordinate system, it's just the distance from the pole to your point. So we'll call that the polar distance. Theta is an angle. It's a direct angle, the usual direction, positive is counterclockwise, from the polar axis to the ray through the point R. So these two numbers together, the polar radius and the polar angle, also determine the location of a point. So they're an alternative coordinate system, and we call that coordinate system the polar coordinate system for the plane. All right. So if we superimpose those two pictures on top of each other, what does that mean? I'm going to sort of draw one picture on top of the other. And when we do this, we'll always make the following convention, that we put the pole at the origin in the XY plane, and we do it in a way that the polar axis becomes the positive x-axis. All right, so we'll make that convention now, and I'll never deviate from it. So here's the picture. You can see I've done it. I've got my polar axis superimposed right on top of my x-axis. The pole is at the origin. The y-axis is perpendicular to the x-axis. And I've picked a point here. And I'm writing that point's rectangular coordinates, x and y. You can see I've marked them in the picture. I'm writing its polar coordinates, r and theta. I've marked them in the picture. And I'd like to be able to convert. I'd like to be able to take the say, for example, polar coordinates of this point and tell you what the rectangular coordinates are. So we're going to do that with some elementary trigonometry. If I kind of highlight this right triangle I'm looking at, one of its legs is length x, it's got another leg of length y, and it's got a hypotenuse that has length r. And I'm going to focus on that angle theta like it's shown there. And using some right triangle trigonometry, well, the cosine of theta is the adjacent side's length to the hypotenuse side length, the ratio of it, I mean. And if you solve that for x, you get that x is equal to r times the cosine of theta. Likewise, using the sine of the angle, you get that y is r times the sine of theta. And so that's half of our conversion work. If you want to convert a point from polar coordinates to rectangular coordinates, those two formulas are how you do it. You do it with those trigonometric functions. Let's try it. Let's try it a little bit here. I've got a polar point. I have to emphasize that it's a polar point because I need to know, does this number say 2? Does it represent an x value or an r value? Well, I've told you it's an r value. So just to try these formulas out, this is just kind of a trigonometric exercise. To find x, you have to take 2 and multiply it by the cosine of pi over 3. To find y, you got to take 2 and multiply it by the sine of pi over 3. All right, you can check a unit circle or use a calculator. The cosine of pi over 3 is a half. Its sine is square root of 3 over 2. 2 times a half is 1. 2 times root 3 over 2 is root 3. So the rectangular coordinates of this point, I didn't really leave myself enough room to write my answer. Let me just do it over here. The rectangular coordinates are 1, comma, square root of 3. So you're more used to the rectangular coordinate system. You know that's a first quadrant point. X is 1, y is square root of 3. Its polar coordinates are 2 pi over 3. Let's do the same thing for this point. This point has a negative angle, but the formulas don't care. You take the cosine of minus pi over 4. Okay, it's the same as the cosine of 7 pi over 4 if you want. Do the same thing for the sine. The cosine of pi over 4, the cosine of minus pi over 4 is 1 over root 2. Its sine is negative 1 over root 2. So this time the x coordinate of our point is going to be 3 over root 2, and the y coordinate is going to be the opposite of that. All right. So once again, if you want to write the rectangular coordinates over here as a summary, they look like 3 over root 2, comma, minus 3 over root 2. Sweet. So if you have those formulas in front of you and you can evaluate the sine and cosine functions successfully, you can convert points from polar coordinates to rectangular coordinates. All right, let's try to go the other way. I've just recycled our picture here. So this time we're going to be using a little bit of Pythagorean theorem. The radius is the length of that segment that I just colored yellow there, and that segment, well, it is the hypotenuse of a triangle whose legs are x and y. So the Pythagorean theorem says that x squared plus y squared is r squared, and if you solve that for r, then you get that it's the square root of x squared plus y squared. So that's how you recover the polar radius. It's just the distance formula, because the polar radius is just the distance from the point xy to the origin, 0, 0. We can also use some trigonometry. The tangent of that angle theta there, well, if x isn't 0, is y over x. And so theta is the inverse tangent of y over x. You'll see I'm putting some quotes around that formula. I usually don't see that in mathematics. It just means that you need to be a little bit careful. That formula is kind of morally correct, but depending on which quadrant the point is in, if you were using a calculator, for example, to find that angle, you might not get quite the right answer. I just want to show you what I mean by that by some examples below. Here I'm kind of giving a hint. I'll just remind you that the inverse tangent function never gives you an angle in the second or third quadrant. It's always a fourth quadrant angle as a negative, or a first quadrant angle. So that's kind of why those quotation marks are there. But passing over that little detail for a second, let's just say that, yeah, this is mission accomplished. This is how we'll convert from rectangular to polar. I'll kind of warn you a little bit about what to do with that inverse tangent function in our examples. Okay, let's try it out. Let's see if I can leave that visible there while we try this one. Here we're given a rectangular point, 7, 7. So that's an x value and a y value because we were told this point is rectangular. Okay, you want the polar radius. Polar radius is the square root of 7 squared plus 7 squared. That's going to end up being, what, 7 times the square root of 2 after you simplify it. So that's its polar radius. How do we find the angle? Let's just take a chance on this inverse tangent function. We have to take the inverse tangent of 7 over 7. That's the inverse tangent of 1. That's the angle pi over 4. So the polar coordinates of this point, sorry, I didn't leave a lot of room to write these here. The polar coordinates are radius is 7 root 2, angle is pi over 4. Cool. Let's do another one. This one I want to say something about we have to proceed with a little bit of caution and kind of explaining what I mean by those quotation marks above, because here my x coordinate is 0. The formula that's in the box formula won't allow that. All right, but all is not lost. All is not lost. Let's draw a little picture of the xy plane. Pictures are always helpful. I know where the xy coordinates of 0, 3 are. It's right there. So I can still compute the radius. It's the square root of 0 squared plus 9. It's the square root of 9, that's 3. But this formula up here, I can't use it to compute the angle because x is 0. But I'm not confused about what the angle of that point is. The angle of that point is pi over 2. I don't need a formula to tell me that. The angle's on the positive x-axis. Any point on the positive x-axis is going to have an angle that's pi over 2. We don't need a formula for that. So if x is 0 and you want to know what theta is, just draw a picture. If x is 0 and y is positive, then theta is pi over 2. If x is 0 and y is negative, well, what's theta going to be in that case? You could take it to be minus pi over 2 if you like. You could take it to be 3 pi over 2 if you like. We'll talk about this a little bit further down the road. But yeah, polar coordinates, unlike rectangular coordinates, they're not unique. All right, so what's the point of my second example? If x is 0, don't worry, the angle is visibly either pi over 2 or 3 pi over 2. It just depends on which part of the y-axis you're on. Okay, let's try this one. This one's also sort of a cautionary tale. Let me tell you why. Let me draw a picture before we get started here. If I visualize where this point is, minus 1/2 root 3 over 2. Let me visualize it like it's right there. It's a second quadrant point. So the angle that I'm looking at here, it looks like that. That's my theta. We can compute r. R is the square root of, well, 1/2 squared plus square root of 3 over 2 squared. So that's the square root of 1/4 plus 3/4. That's just 1. So this polar radius is 1. But now let me just see what my calculator is going to do. If I take the inverse tangent of y over x, so that's the inverse tangent of root 3 over 2 divided by minus 1/2. You can type it in like that into your calculator, or if you like, you can simplify this. It's the inverse tangent of pi over 3. You can pause this video and get your calculator out, make sure it's in radian mode. But when you do it, your calculator is going to tell you that the inverse tangent of pi over 3 is minus pi over 3. Or as a decimal, it would be a little negative 1 point something. Well, that can't be right, because minus pi over 3 is an angle that's in the fourth quadrant. Sorry, I just wrote the wrong. Can't say 3 while I write 4. Minus pi over 3 is an angle in the fourth quadrant. Remember, we were warned, the inverse tangent function will always do this. The inverse tangent function is always going to give us a function or an angle that's in the first or fourth quadrant. So how do we reconcile this? Well, we just have to remember that this point we were given had a negative x coordinate and a positive y coordinate. There's a point where the stuff is opposite to that. If you take 1/2 x minus root 3 over 2, you get the same ratio. And the inverse tangent function thinks that we meant that point. So when this happens, you have to, as a human, you have to remember to take your calculator answer and, well, increase it by pi. We're exactly off by a half turn. So the real angle is minus pi over 3 plus pi, or 2 pi over 3. All right? So we'll talk more about this, but when you are using the inverse tangent function to find the angle of a polar coordinate, that's what these quotation marks mean, is if your point is in the second or the third quadrant, then you have to take your calculator answer and increase it by pi. All right, we'll talk about it in class. Good. So continuing along here, let me just try to make that a little bit less busy. I've already kind of mentioned this, that rectangular and polar coordinates are different for many reasons. And among the biggest one is that in rectangular coordinates, a point only has one coordinate. There's no such thing as sort of like a different x and a different y that locate the same place in the plane. But in polar coordinates, that's not true. In fact, there's a lot of stuff that can go on here. Let's look at this first line. I'm highlighting it now. What is it saying? If you visualize this point r theta, I've drawn it there for you in the plane. If you increased theta by a whole number multiple of 2 pi, let me indicate that there. I've drawn theta in the picture. Let me show you theta plus 2 pi. Well, you go all the way around. Well, theta plus 2 pi, it locates the same point. Or if you did plus 4 pi or plus 6 pi, or subtract 2 pi or subtract 4 pi, you're just doing a whole turn. Well, when you're done doing a whole turn, you're looking in the same direction. So it's never going to be, it never happens in rectangular coordinates, but in polar coordinates, you can have different angles giving you the same point. If you always take your angle between 0 and 2 pi, then it's kind of unique, but we don't want to make that restriction. Another thing that can happen is that if the radius is 0, you're at the pole, well, then it doesn't matter what the angle is. If you have no distance from the origin, then no matter what direction you're looking in, quote unquote, you're still at the origin. So that's kind of a difference. And then this last one, I actually want you to think of it as just a definition. Don't try to reason out why it's true, but we do want to allow for negative radii. It makes the theory that we're going to look at with functions easier. We don't want to insist that the radii be positive. But if the radius is negative, it can't represent the distance to the origin because distance cannot be negative. So the convention is that if you have a negative radius, you mean that it's like the positive radius, but the angle is the other way. So you have to increase theta by pi. So I'm showing you here in this picture, I've got my r theta. Well, if I increase the angle by pi, I could write that with a negative radius. Yeah. So even though theta is a first quadrant angle, if the radius is negative, I would be in the third quadrant there because I go the other way. We'll get used to it. Okay, so this video is getting a little long. Let's see if we can't wrap it up with something that we can think about before we meet, and then we'll talk about functions. So here are some questions. If I pick a constant number, my question is, well, what would the graph look like if I just let r be that constant, but I didn't, or I allowed theta to take on any value? And conversely, what about setting theta equal to 0? So kind of what I'm wondering about here, if you like, is what does polar graph paper look like? And you might say polar graph paper, what are you talking about? What is graph paper? I didn't save a lot of room here. I'm just gonna kind of ruin the notes, but when you draw a graph paper, what are you doing? You're drawing, say these vertical lines. Well, that's x equals a constant, x equals a constant, x equals a constant. You're just drawing equally spaced values of x to make it easy to see how to count. Likewise, these horizontal lines, y is a constant along any of them. So graph paper in the rectangular plane is just a picture of what it means to set one of the x coordinates equal to a constant. That's how you get your vertical lines, or how to set y equal to a constant. That's how you get a horizontal line. So basically, I'm asking the same questions here in polar coordinates. What if I set r equal to a constant? What if I set theta equal to a constant? Well, let's look. Maybe you saw a little peek when I scrolled too far. I'm going to kind of shrink this picture a little bit so you can see it all. Hopefully it's not too small on your screen. So I've drawn here, and you can kind of see the x-axis in my picture. I'll mark an X right there. This is the y-axis. There's your origin. I've just drawn several concentric circles, and let's see why. Right here, this is a circle of radius 1. And if I keep r equal to 1, but I allow theta to change, well, then I could get any point on this curve that I'm highlighting, yeah? So that's a picture of what it looks like to fix r and let theta vary. In fact, every one of these circles is a picture of what it looks like to fix r and let theta vary. So the answer to my first question up here, what does the graph r equals a constant look like? The answer is it's a circle. It's a circle centered at the origin. Yeah, with radius r0. What are these other things? If we fix a value of theta, say pi over 6, we fix a value of theta, I can let r be anything it wants, so I'll get that spoke. And if I allow negative r, this is a little tricky, listen carefully when I say it, here I'm coloring points where theta is still pi over 6, but r is negative. Remember, when r is negative, you go the other way. So theta equaling constants looks like lines through the origin. Theta being constants are lines through the origin. So you draw a bunch of concentric circles and you draw a bunch of lines through the origin and you get yourself a piece of polar graph paper, right? You can Google, if you want, polar graph paper, and you'll be led to PDFs where you can throw them on your tablet or your computer. And if you have some way you can plot these points in your homework on this, it makes it really a lot easier. I'm going to get rid of these colors here so we can kind of clean up our picture, but you can ask me if you have questions about what I mean by polar graph paper. So what I would like to do is some exercises where I want to use this paper. I don't know how I'm going to do this because the resolution's not that great, but let's see if we can try to do it here. So let's start by practicing just plotting some points. Some of your homework is going to be stuff like this. I want to just plot some points. These points are all polar. I should have emphasized it. They're all given in the polar coordinate system. So let's just do it one at a time here. So the first point is 2 comma pi over 2, all right? So 2 comma pi over 2 means that the radius is 2 and the angle is pi over 2. So where is that point going to be? 2 comma pi over 2. Well, the circle of radius 2 is green. Pi over 2 is on the positive y-axis. So there's the point, 2 comma pi over 2. All right. Let's just color code these as we go. So how about minus 2 comma pi over 6? Sorry about all the scrolling here. I'll try to figure out some better way to do it, but I'm just going to go with it for now because this video is getting long. Negative 2 pi over 6. Well, I can see where pi over 6 is. Pi over 6 is, sorry about that, this spoke. You can see it. But if I have a negative radius, I have to go the other way. So I have to go out the opposite spoke 2 units away from the origin. All right, so you can ask me about this in office hours. I'm going to write minus 2, even though pi over 6 is a first quadrant angle, negative 2 pi over 6 is a third quadrant point because negative radii make you go the other way. All right. Finally, what's a fun color here? Blue. How about 5 pi over 2? 5 pi over 2 is bigger than 2 pi. So 5 pi over 2, well, you'd have to go all the way around once plus another pi over 2. So the point 2, sorry about that, the point 2, 5 pi over 2, it's the same as 2 comma pi over 2. Right? So this is where polar coordinates sometimes can get a little bit fuzzy to think about because the angles, the numbers pi over 2 and 5 pi over 2 are not the same. But these 2 points are the same because the direction pi over 2 and 5 pi over 2 are the same. Namely, they're both pointing up the positive y-axis. Okay? So you can try some exercises like that. Get yourself some polar graph paper and plot them. The last thing I want to do is something like this. Let me try to put this up here where we can see it at the same time. So So I want to try to shade the area. Can you still read that? Shade the area where r is between 1 and 3 and theta is between pi over 6 and pi over 3. All right, let's pick a color to shade it in, something bright. So theta between pi over 6 and pi over 3. Well, theta being pi over 6 is right here. I have positive radii, so I'm going to stick in that quadrant. Theta equaling pi over 3 is right there. So we're going to take thetas between those. And then r equals 1. Well, r equals 1 is that circle, if you can see the 1 there on the axis. R equals 2 is this guy. So the area where r is between 1 and 3 and theta is between pi over 6 and pi over 3, well, it's this little wedge-shaped thing. Yeah, that's the area where r is between 1 and 3 and theta is between pi over 6 and pi over 3. One more, and then we'll end this long video. Let's choose another sort of super bright color here. How about r between -3 and -1 and these theta ranges? So negative radii, we are on alert because it means that all of the angles are going to change. All right. So when I'm thinking about 7 pi over 6, well, 7 pi over 6 is right here in the picture. Yeah. But I'm actually going to go out the other way because of the negative radii. Likewise, 4 pi over 3. 4 pi over 3 is right there. I just colored it. But I'm going to go the other way because of the negative radii. So I've already accounted for the opposite direction. So now I swap out r is between 1 and 3. R is between 1 and 3 because we've already accounted for the directions. And so you can see that this region, it's actually the exact same. It's actually the exact same region. Why is that true? Because of this negative radii. Okay, so that is a not so quick introduction to the polar coordinate system. Make sure that you look at the activity. Make sure that you do the book homework. It's more important than ever that you do all of those problems. Check them on Slater, check them with me. You're not doing them for points, you're doing them to learn how to do this stuff so that when you take your exams, you're confident and you've had a lot of practice. All right, so I'll end this video here and I will see you in a Zoom meeting in class.